So hello everyone, welcome, good morning, good afternoon. Lectures Without Borders and Your Planet are pleased to welcome all of you for today's paired presentation on volcanoes on Earth and beyond. So we have today two speakers, as is the point of the paired presentations. We have Dr. Juan Manuel Albite, who is a volcanologist specialized in volcanic risk, and who is a postdoctoral fellow researcher at the University of Buenos Aires in Argentina. We also have Dr. Hans Huybrighs, if I pronounce it correctly, almost, who is a research fellow at the European Space Agency, ESA. He studies the moons of Jupiter, Io, and Europa as part of his research. So today we are going to hear a presentation of something like 20 minutes long, and then we will be receiving and answering questions in English. If the public is interested, we can finish with questions in Spanish, but I don't think we have in the list of attendees anyone speaking Spanish here. But just in case, please raise your interest in the chat and we'll be happy to continue in Spanish with Juan. Okay, so with that, I think we can start. So Juan, if you want to start for us, you're free to go.
Yeah, thank you, Ulysse, and hello everyone. So I will share my screen now. Great. I think it's okay. No? You can see it. So, Ulysse has already presented me. I'm Juan Manuel. I'm from Argentina. I study volcanoes, active volcanoes. So we will talk about volcanism on Earth. And to start this talk and try to remember some or to understand better volcanism, we have to know where it happens. Earth has different layers, and volcanism is strictly related to crust, obviously, and the magma is originated in the mantle. Both crust and mantle are layers of the Earth, both solid. Crust, obviously, completely solid, and the mantle, if you have ever imagined is like a big ocean of magma. Well, it is not. It's just a solid rock that has like some plastic behavior, like plastilin. And as there is no, except from the outer core, there is no layer that is liquid that is formed by magma, we have to know how magma is formed. Magma is a mixture of melted rock, crystal, and gases. And when it is below the surface, it is called just magma. When it is on the surface, you can call it lava, and I think we all know, we can imagine what lava is, and pyroclastic rocks, another kind of different type of volcanic product that is related with rapid cooling and explosive eruption. But this magma, if there is no liquid layer on Earth or formed by completely by magma, everything is solid, we have to melt it down. So we need to melt the rock to form this magma before it comes out to the surface. And obviously, as Fry says here in this slide, a candle won't be enough. So there must be some kind of process that melts down the rocks of the mantle and form this magma. We all need to have volcanoes. So where are they located? There is some kind of relationship between this process and the location of the volcanoes on Earth. So here in this map, you can see the locations of active volcanoes around Earth. And they are very very scattered around the surface. But there's some of preferential locations. I will show you first this with these blue ellipses. These locations are related to subduction zones, to plate tectonic limits. The subduction zones are zones where the oceanic crust that is more dense than the continental crust or other oceanic crusts goes beneath each other. The oceanic crust more dense goes beneath, for example, the continental crust, and the water that is within it goes to the upper mantle here in this zone. This water is like liberated into the mantle, and these rocks are melted down. It's like some kind of complex chemical process, but this is one of the mechanisms that forms the volcanoes that are located here in the subduction zones. Another type of plate tectonic limits that related to volcanoes are extensional borders, like mid-ocean ridges or rifts. There are two types. The mid-ocean ridges, like big ridges beneath the ocean, like in the central Atlantic, are zones where the two plate tectonics are separating one from each other. This separation leads to a decompression. The mantle, the rocks in the mantle loses pressure and changes its state from solid to liquid, forming magma and forming finally the volcanoes. Most of these volcanoes in these zones, in mid-ocean ridges, are beneath the ocean. That is the reason why there are some less volcanoes than in subduction zones. While the other zone of extensional borders are the rift valleys. That in these places, two continental crusts are separating one from each other, forming also volcanoes. Here you have some examples. We have on Earth now active, the East Africa Valley, the Rift Valley in Africa, and the Nyiragongo volcano, for example, in Africa, is one of these type of volcanic examples in rift zones. But not every volcano is located in a plate tectonic limit. There are also some volcanoes inside the plates that are called intraplate volcanism. These volcanoes, for example, Hawaii or Canarias, are related to a very deep and hot material coming from the lower mantle that goes to the surface and forms a magma. And big volcanoes are called shield volcanoes. There are some examples, for example, of these volcanoes in Mars, like Mount Olympus. It's also a shield volcano. Obviously, it's not active. Here you have Hawaii. The island is completely a shield volcano. All the islands that forms the Canarias are completely shield volcanoes. And as we saw, as there are different types of volcanism, we have to know, of magmatism, we have to know if there is some kind of variations in the type of eruptions related to this these different types of magmatism. To understand it better, there are two big families of eruption: the effusive eruptions, basically lava eruptions, and the explosive eruptions. The difference is how they go out to the surface. The effusive eruption, magma comes out and it doesn't change anything in the middle, or almost anything. But explosive eruptions, there is like in the volcano, before the eruption, there is like a tap in the top of the volcano in the summit. It begins to increase the pressure, and finally it explodes. And this magma comes out like pyroclastic material, like, for example, volcanic ashes. As a consequence, you will have different types of volcanoes. For example, stratovolcanoes or calderas, this one in the left, the typical volcanoes are more related to explosive eruptions, while shield volcanoes, like this in the left, are more related to lava, to effusive eruptions. And then there are these types of volcanoes that are called monogenetic because they only give one eruption in their life, like scoria cones that are common in both types of environments, let's say. Cerro Viejo de la Palma, for example, the ongoing eruption is a lava eruption and effusive eruption related to the shield volcano, to the group of shield volcanoes in the La Palma, in the Canarias Islands. And then you have, for example, the Andes volcanoes that are all stratovolcanoes. So once we have the type of volcanism, the distribution, we have to know how do we study them. So the first and maybe the most important part of studying volcanoes is to know what kind of eruptions will they do and how often do they make eruptions. The first step is studying the rocks, the ancient deposits. For example, if you want to study a volcano, you have to know, well, does it make effusive eruptions or explosive eruptions? How do we know it? Well, how many lava flows are there in the volcano? Or how many pyroclastic deposits, ashes deposits you can see? And how often? For example, you have 3 lavas, and the lava eruption related to this volcano is like the span of time between each lava are 50 years, 100 years, 1,000 years. So this is the most important part, just to know, to predict how it will behave in the future. What kind of eruptions can we expect from this volcano? And then after we do that, the most important part is to monitor them. Once we know they are active, we have to study their manifestations. Like, for example, volcanic gases. The volcanic gases, like you may have seen fumaroles, these like plumes of vapor and acid gases related to volcanoes. Well, you can study their chemical composition, and the chemical composition changes if the magma starts to rise to the surface. And what do? We study these changes in time to know if this volcano is about to make an eruption or not. Another sign of this activation, maybe, of the eruption will be earthquakes. Earthquakes are related to the movement of the magma. When magma rises up to the surface, it starts to break the rock, and this breaking of the rock generates small earthquakes. But there may be thousands of them before an eruption. This video here is an animation of the earthquakes before the Canarias eruption here in the Cerro Viejo de la Palma. 2 weeks before, there were around 10,000 volcanic earthquakes, and then it ended up with an eruption. And the third technique, the most important technique is the formation. Now I have you another animation of the Etna volcano. Why is the formation? Because when magma rises up to the surface, it can deform the surface of the volcano, it inflates. And as you can see in this 9-year span of time in Etna volcano, there were in the summit of the volcano like 15 centimeters a year of deformation. So the volcano inflated before every eruption and then deflated after the magma came out and the eruption ceased. So with all these techniques, we can study volcanoes, and it is important for us to use all of them to understand better volcanoes and to prevent eruptions. And I think with this I'm done, so thank you very much for your attention.
Thank you very much, Juan. Thank you. So From this, we are going to switch to the presentation of Hans, and after that, we will receive your questions. So please, if you have questions, you can start writing them in the chat right now. And yes, Hans, the floor is yours.
I'm assuming you can see and hear me?
Yes.
Yes. So these are the planets of the solar system. And what do you think? Are there volcanoes on these planets, and where could they be? Well, the answer, of course, is yes, there are volcanoes in space. They are on Venus, on Mercury maybe, and definitely on Mars. But there are no volcanoes on Jupiter, Saturn, Uranus, and Neptune. These 4 big planets, they are made of gas and not of rocks like the other planets. So because they're made of gas, they have no volcanoes. But I'm going to talk about Jupiter anyway in this talk, because at Jupiter, we have some of the most interesting volcanoes that we know of. And they're not on Jupiter, but they're on moons of Jupiter. Jupiter is a planet with a lot of moons, and some of those have volcanoes. And 2 of those are called Io and Europa. And I call them the moons of ice and fire, because Io has lava volcanoes and Europa has cold volcanoes of water and ice. So in this talk, I'm going to speak about what kind of volcanoes there are in space, what are some of the things that cause them, and how scientists are studying the volcanoes. Just quickly about myself before I begin. So my name is Hans. I'm from Belgium, small country in Europe, and I live in another small country now in the Netherlands, and I work for the European Space Agency. So it's a large organization in Europe that does everything related to space, from training astronauts to going to explore the planets of the solar system. And I work on a new space mission that will go to Jupiter to study its moons. Back to our first topic. So what kind of volcanoes exist in space? So very broadly, as I already said, there are hot volcanoes of lava, like on the moon Io, but there are also cold volcanoes that don't involve molten rock, but water and maybe ice. And we find that on Europa. That's what these 2 moons look like. And you can see them next to Jupiter on the left. You see just a part of Jupiter. That's because it's such a large planet. Jupiter is really big. And you might think that Io and Europa are small, but that's not the case. They're about the same size as our own moon. So pretty big moons. And let's go to the first one, Io, the moon of fire. So I call it the fire moon because it has a lot of volcanoes. Actually, it's the most volcanically active object in the solar system. And its whole surface is full of volcanoes. All these specks and rings that you can see everywhere, those are volcanoes. I'm going to make that even more clear with another picture. This one. This is a picture of Io, but not with the light that we usually see, but the heat radiation. So what you see here, these bright spots, are all kinds of places on Io where it's very hot. And you can see that there are everywhere these spots where it's very hot. And each of these very hot spots is a volcano that's erupting on the surface of Io. So they're everywhere and they're going on all the time. So it's full of volcanoes on Io. And these volcanoes, what do they look like? They're not mountains like we often have on Earth, but they're like large lava lakes. And this is one of those lava lakes, and they're really gigantic. To give you an idea, if I would put the city of New York next to it. So this is the island of Manhattan in New York with all the famous skyscrapers. And you can fit that whole island at least 4 times in this lava lake. So really, really big. And when these lava lakes erupt, you can see it from very far. Here you see Io, and on the top of Io, you see something happening. It's a fountain of gas and stuff coming out of the volcano and falling back on the surface of Io. So you can see the eruption happening there on the north. And it might look tiny, but this eruption that you're seeing is really large. This is another picture of such a volcanic cloud. It's more than 100 kilometers high. To give you a feeling of how that is, I'm going to put an Earth volcano next to it. There it is. You can probably not see it. It's because it's so small. This is the Eyjafjallajökull, a volcano in Iceland. It's very famous because 10 years ago when it erupted, it made so much gas and such a big cloud that the air traffic in Europe and further was stopped for days. So it's quite a volcano, and that is only 10 kilometers high. So that's tiny compared to the Io volcanic plume. And so when they erupt, a lot of gas and dust is coming out and is falling back to the surface. And it's actually sort of painting the surface of Io. All these colors that you see, the yellow and the red, is coming from the volcanoes. It's sulfur.
Hans, I'm sorry, we lost your sound for some reason. I can't hear you. Nope.
And technically your mic is on.
Yeah.
You're back.
Sorry for the technical hiccup here. My dock has disconnected from the laptop spontaneously.
It's okay, we hear you now.
Okay. Can you confirm that you can hear me properly now?
Yes, we do.
Yes.
Okay. I hope it's still working. Can you remind me what the last thing was that you heard me say?
Maybe start at the beginning of this slide, actually.
Okay, I cannot hear you anymore. This is not going well.
Was the volcano in Iceland that was...
I would say just start at the beginning of this slide. This is where you were approximately. Go. Hans, can you hear us?
Okay, can you hear me?
Yes.
Okay, now I have to hear you as well. Can you say something again?
Can you hear us, Hans?
Yeah, I can hear you.
Okay.
And now we're back with the slides.
Mm-hmm.
Yeah. Where did I leave you off last?
Can you start at the beginning of this slide, maybe?
Yes. So what I was saying here is that this is the surface of Io, and we see a lot of different colors. It's like a weird painting or a strange pizza. And these colors are caused by the volcanoes because the stuff that that comes out of the eruption contains sulfur, and that is what causes the yellow and the red colors. And we can see this painting on the surface of Io change all the time. For example, here we see one of the volcanoes. The volcano has erupted. It has made this red ring around it. And just a few months later, when we pictured it again, it looked like this. There was like this black blob on top of it. That's a second volcano that's erupting and painting over the first one. So all the time we see the surface of Io change between the eruptions. Then the next moon, the moon of ice, Europa. So I call it the moon of ice because its surface is made of ice. That's why it's white. It's a bit dirty ice, so not completely white. And interestingly, under the surface of Europa is an ocean of liquid water. So under all the ice that you see, there is water everywhere. And sometimes that water can get out through cracks in the ice. And then you get sort of cold volcanoes of water that's erupting and freezing immediately. So like a cold volcano of ice and water. And to imagine what that's like, you can think of a bit like the geysers that we have on Earth. It's not quite the same. The geysers on Earth are much smaller, but it might help you imagine a little bit what I'm talking about, what I mean with a cold volcano.
And there's actually a lot of water on this moon, Europa. These two blue balls, they show the volume of water on Europa and the Earth. And you can see that the ball of Europa is actually bigger than the one on the Earth. And that's because the ocean of Europa is so deep, 100 kilometers deep. That's much deeper than the oceans on Earth. Because of that, it has actually more water than there is on the whole surface of the Earth. And liquid water, that's very exciting, because where there's liquid water, there could also be life. We don't know if there's life in the ocean of Europa. We don't know if there are sea monsters or fish. There might not be any animals like that. It might be they're just very simple life forms like bacteria at the most. But even that we don't know about. And you'll hear more about those on the 22nd of November when there is another talk about these small, strange life forms that can live in really weird locations like the ocean of Europa. So another question, what causes the volcanoes? So that's on Io and Europa, at least. It's an interesting question because it has to do with the gravity of Jupiter and the way that Europa and Io go around Jupiter. So these moons, they go around Jupiter, but not in a perfect circle, but an ellipse. And that means that sometimes they're far away from Europa, like you see here. Europa is far away, but it can also be closer by Jupiter while it's going around. And at the same time that they're going around Jupiter, the gravity of Jupiter is also pulling on the moons. And the pulling of Jupiter is so strong that it can change the shape of the moon. It's a bit like, imagine this is one of the moons, and the gravity of Jupiter is pulling on it. It's kind of stretching the moon from a sphere to a rugby ball. You also see here on this drawing. So Jupiter is pulling on the moon and stretching it. But at the same time, the moon is still going around. And at the point when it's closer to Jupiter, the stretching is stronger. And when it's further away from Jupiter, there's less stretching and it's more like a ball. So the effect is that every time Europa goes around Jupiter or Io, the shape changes from sphere to rugby, sphere to rugby. It's kind of like Jupiter is really kneading the moon. I'm gonna go back. Oops, that's the wrong direction. So you can really see like far away, sphere, close by, stretch like a rugby ball. And that causes the Jupiter actually kneads the moons, and that kneading causes friction on the inside. And friction, that's the same thing that happens when you rub your hands together. If you do that really quickly, rubbing your hands together, they get warm. And the same is happening in these moons. The friction that's caused by all the kneading causes heat to be created in the insides of the moons, and that keeps them warm. And in the case of Io, that causes the rocks to melt and the volcanoes to be created. And in the case of Europa, it causes the ice to melt into water, and it also causes the ice to break, all that kneading, all that motion, and through these cracks, the water can come out. And so how do we study these volcanoes? So Juan showed us how he studies volcanoes. He goes to them. And of course, ideally, we would like to do the same. We would like to put Juan on a rocket and send him to Io. But that's maybe not so much fun for Juan because it takes years to go there. It's also very dangerous, not a lot of fun. And it's super expensive. Not even Elon Musk can send Juan to Io or Europa. So what do? We build a robot or a satellite, and we shoot it to the moons, and that will do the research for us so that we don't have to send a human there. And I'm working on a space mission that's called JUICE, Jupiter Icy Moon Explorer. It's a spacecraft that we're building and testing at the moment. This is a picture from earlier this year when the spaceship arrived at the space agency where I work. It's in the big box behind me. This is what's in the box. And here you see it completely unwrapped. So that's our spacecraft or robot that's going to Jupiter to study the moons for us so that we don't have to go ourselves. And one of the cool things that we could do when we get there is fly through one of these water volcanoes on Europa and maybe catch some of the water to figure out if there are traces of life in it. But we have to be patient because the launch is only in 2023 and it will take almost 8 years to get there. So 2031, that's a long time we still have to wait before we can do this. But in the meantime, next time you look out at the stars, remember the moons of ice and fire. Thank you.
Thank you very
Thank
much.
you very much.
Ulysse, are you back
Very
here or
much.
shall I?
I am back. I'm having some difficulties with my internet connection right now, but I am back. Sorry for that. So now the floor is open for questions. So please ask any questions you might have for our two speakers now.
You can use both
In the chat.
or
Let me just reply to them. So, yes, chat and Q&A. Oh no. Can you hear me? I think I might have lagged again. Juan, can you hear me?
I can hear you,
Yes.
Ulysse.
Oh, okay.
Yes.
So Juan, I was saying that when you're studying volcanoes, you're trying to learn about the type of eruptions, the frequency. Do you know if those change over the life of a volcano?
Yes, this may change. Yes.
Okay, so that means that even if you study what happens in the past, is that good enough for prediction of the future or not?
It's better than not knowing anything. Yes, I have, for example, Copahue volcano, the volcano I'm studying at the moment. In the recent times, the 20th century, all the eruptions were like very, very calm, like small column and a small plume and no lava involved. But in the past, there are like deposits as big as, I don't know, like with an enormous volume of rock that was related to an eruption of Copahue volcano or the pre-Copahue volcano. So we just don't know if that can happen again. It's like a low probability of that happening again, but we cannot discount this hypothesis. So it may change around time. Another example I can think of is, for example, now the Cerro Viejo de La Palma. The most long-lasting eruption was 45 days, and I think we are about to break that record. So you can never know with a volcano, but the past is important. Yes.
Okay. Well, it is fascinating to see them breathe. Actually, that video you had of them just breathing in and out, it was just like, oh, okay, this is really happening. That's crazy. And Hans, I do have a question for you too. So you said you were working on the JUICE mission. In such like huge scale mission, is the plan for the probe already completely settled, or is it still a matter of discussion? And how long can it be discussed before deciding what you want to do with the probe?
That's a good question. I think it's definitely not settled yet. The planning, developing the planning of what you're going to do exactly is something that can take a few years to get it right. So we are already starting with it now, but it will take some more years to really finish it. And some of the reasons why it takes so long is that we have a lot of instruments. Like on the spacecraft, there are 10 different scientific tools that all want to measure something different about the moon. One wants to take pictures, one wants to take samples of particles that are flying around. So we have a lot of different instruments that want to do something different. And sometimes they don't want to do the same thing. For one instrument, it's best to look in that direction. For the other one, it's best to look in the other direction. So you might have conflicting demands, and then figuring out what's really the best thing to do for everyone and how to do it exactly and at what time precisely is something that takes a lot of time to figure out. So that's something that's going on now and will take still some years to finish.
Okay, so it's like finding the best compromise between all the instruments and all the teams and everyone, so that they can be the better used and optimized.
Yeah, between between the teams for sure, but also between what's technically possible, because you only have this much electricity that you can spend, and you can only send so much data back to Earth. So those are also things that you have to think about when you're making the planning, and that makes it extra complicated.
Interesting, thanks. Okay, so we do have questions in the chat now. So let me see. We do have a question about how is it possible for a volcano to be active for 45 days? So maybe that's a question actually for the two of you, because it might be depending on the kind of volcano. So who wants to go first?
For me, it's the same. I don't know, Hans, if you can.
So go for it, Juan.
Okay. Basically, there is no limit of time for eruption to last. It depends in the amount of magma related to the volcanic system. For example, in a system like Canarias or Hawaii, the volume of magma related to these volcanoes is enormous. It's constantly forming in the mantle and constantly rising up to the crust. So if the conditions are basically the planets are aligned, let's just say, like this is just a figure of speech. I think the eruptions may last very long, and this will be not the record in the world. For example, the Paricutin volcano, that is a scoria cone formed in Mexico in the 40s, I think, in the 1940s, lasted 11 years. So 11 years eruption that formed a 400-meter tall volcano, and then it stopped. So this is just very relative, and as soon as there is enough magma forming, the eruption may last, I don't know if forever, but very long.
Wow, yeah, 11 years, that's crazy. Do we have, Hans, do we have an idea of how long the eruptions are lasting for on Io?
That's a good point. I would say that Io is active all the time, just because there's heating, the kneading thing that I was talking about, that's going on all the time. Io goes around Jupiter every 1.5 days, so it's constantly being warmed up. There's always heat, and so there's always activity. And as I showed you the map with the hotspots, like there's always something going on. That doesn't mean that each individual volcano is erupting all the time. Like they can be they're not, each individual volcano is not active all the time. They last a certain time. And I think that can also take several days, perhaps even longer, but I'm not quite sure how long that is for these volcanoes.
Okay. Anna is asking it's about the eruption of the Eyjafjallajökull in Iceland 10 years ago. Why did it stop the flying across Europe, and what damage did it do, and what damage can a volcano do?
Okay, yes, I have troubles pronouncing this French volcano. You can understand I'm from Argentina, this is Iceland, but it's not restricted to this volcano. It's for every volcano that gives birth to a big plume of pyroclastic material. This pyroclastic material, the ashes, are very, very small, like less than 2 millimeters of diameter, and they are suspended in the atmosphere. So if a plane goes through this plume, the ashes may melt inside the turbines of the plane, and the plane may fall because it's just it happens in the past during, I think, the beginning of the 20th century. There was some plane accidents related to volcanic eruptions. So there is a world politics that as soon as there are suspended volcanic material in the atmosphere, the flights are suspended completely. Here in Argentina, it happens relatively frequent because we have many volcanoes in the southwest of our country, and the traffic was interrupted very, very often in the last 10 years because we had 4 eruptions, I think.
Okay, well, thanks. So I have a question from Pavlik saying, do you have to be really close to the volcano to study it? Or can you be far away, like in another city or even country? And I think this one, Hans, you can answer. Could we apply, because for JUICE, for instance, we have to be far away. We are far away by design. So is it something we could do also for Earth, do you think? And maybe Juan, you can complement that afterwards.
For sure, you can study the volcanoes on Earth from space with that volcano that's erupting right now on the Canary Islands. One of the things that's being done is to monitor from space where the hotspots are and how the lava is flowing day by day. Those are things you can do very well from space with satellites. So for sure, you can study volcanoes on Earth from space. Okay. And perhaps Juan wants to add something to that.
I think it depends in what subdiscipline of volcanology are you studying. Like, for example, I study rocks, so I have to go to a very, I think, safe place around the volcano. I usually go to the active crater, to the summit of the Copahue volcano. It's a volcano I study, but it depends. There are people that, for example, goes by the lava flow and takes a sample from the lava, from the hot lava, and takes to the laboratory to analyze the composition. And all these techniques like seismology or deformation may be done with remote sensing, with the satellites. All the satellites that are around Earth are measuring different types of signs that are useful to study the state of activity of a volcano. So it depends, and there are direct techniques and techniques with sensoring with remote sensing. So you don't strictly have to be very close to the volcano to study it.
All right, thanks. So let's go with another question from Panagiotis, who is asking if more than one volcano erupts in the oceans, what would it cause to happen? So I think it's related to submarine eruptions. So what's the effect of that?
It depends on the eruption and the volume of the eruption, the explosivity of the eruption. Submarine eruptions are happening all the time while we talk, when we speak. So not necessarily are very important. But if like a very big volcano starts an eruption right now in any part of the ocean, it may cause, for example, changes in the current dynamics of the ocean because it changes the temperature, the composition of the water because of the acid gases related to volcanoes, and in very extreme and rare cases, it may cause tsunamis. There are some tsunamis related to volcanic islands in the ocean. Like, for example, Santorini, that was an active caldera when it erupted in the past. I don't remember exactly when. I think that's in the Middle Ages or maybe before. the destruction was amazing. And there are some like mythological stories related to I don't remember the name of this civilization that is the Atlantis, related to that the Atlantis were living in Santorini before Santorini erupted.
All right. So maybe to end this session, because it's already running late, I have a series of questions.
All the last questions that we have received, but let's say that from now we will not accept more questions, just like the last one to come, and we will answer everything we have.
Okay. So let's see. Maybe we'll have one more question about, yeah, we have two questions about volcanoes in particular, and then it's more about what inspired you to become scientist and etc. So let's go with the volcanoes questions first. So we have two. We have one that is, can lava come out of unexpected plates, like a middle of the plate? So I think that's something you talked about, Juan. And what do you think about the Yellowstone caldera volcano?
Unexpected places, not so unexpected, I think. Intraplate volcanism is, we know where it is, and it may lead to the creation of new volcanoes, but in some kind of places, not so unexpected, as I said before. Or for example, in the east rift of Africa Valley, that now the African plate is separating. Like the first stage of this separation of plates starts with unexpected volcanism in some kind of place. And this volcanism leads up to the separation of the plates. So in some kind of, then in any volcano, like for example in La Palma didn't erupt from the crater summit of the main volcano, that is the Teneguía. It erupted by from the one of the slopes of the volcano, for example. This is something that may happen. And related to Yellowstone, Yellowstone is a very, very super volcano that is currently active, but is not expected to end up with a very, very big eruption, because the amount of magma related to the volcano that can go to the surface is really, really small compared to the big magma chamber related to the Yellowstone eruption that happened 600,000 years ago. So there are lots like, I think, like some news that are not very strictly scientific data. So you can visit Yellowstone and see the geysers. I am planning to do it in any time in the future, because I already don't know Yellowstone.
That is a good news. Okay. So let's end up with the questions from Marina, who asked, what inspired you to become scientists and study volcanoes? What were your favorite subjects at school? Where did you study? Which university? So the both of you can answer that question and we can end up with these.
Hans.
Yeah, I'll go first. What inspired me more generally, what inspired me to study space is already when I was a kid. When I was 6 or 7 years old, there was a comet in the same year that the first little Mars vehicle landed on Mars, and I saw that comet myself, and I read about the little Mars rover going about on Mars, and I got really inspired by those things, and that's what made me interested in space. And that eventually led me to choose to study something related to space. And My favorite subject, yeah, at school, we didn't learn about space much. That was a bit disappointing for me. I really wanted to learn about space, but it wasn't really important in school, so that was rather disappointing. But to learn about space, I then went in my own time to an astronomy club, and that's where I learned what I wanted to learn. And then as an adult, I went to study aerospace engineering. So I learned how to design spaceships in Delft, in the Netherlands. They have like a university that's specialized in that stuff. And that's where I finally learned about spaceships and planets, and got to study what I really wanted to do.
Right, thank you.
So in my case, I had the opportunity to travel with my family around here, Argentina, my country, that is very big and has lots of landscapes that are almost breathtaking in some cases. And I think that inspired me to learn how, so why there are mountains here, how do you find a fossil in 300 meters above the ocean, and it's a fossil, and those kind of things really inspired me. I think that at school, I was very nerdy in my in my teenage time. I like almost everything, but all like chemistry, physics, maths, also geography were my favorite subjects. And then when I had to decide what career I wanted to study, I had three options. I was between being a geologist, or being a meteorologist, or an oceanographist. And I decided geology because I thought that I could learn about almost everything in nature science related to Earth. And then during the university, volcanoes fascinated me, and I think that they were very interesting. And here in South America, or at least in Argentina, because in Chile or Colombia or Mexico, there are quite lots of volcanologists studying and observatories of volcanoes. But here in Argentina, this subject is not very common, and we need to study our volcanoes. So now I'm here studying them, and very happy about that.
All right. Thank you, Juan. Thank you, Hans. That was an excellent paired presentation. We are really happy that we started our event with you. Really exciting, and we had a lot of questions from our attendees. So thank you very much for the questions too. Anastasia, do you want to conclude with some words?
I just want to thank both the lecturers. It was very interesting, and the attendees. Thank you, teachers and students, for joining. And we will come back with the next live talk next week. So please stay with us, and for sure we will share the recording of the webinar with all registered participants. So thank you once again, and I wish you a good day.